You recall yesterday we discussed functions and equations. In today's lesson, we're going to graph functions. Functions can be graphed on a coordinate plane by A, creating an input-output table, B, forming ordered pairs, and C, plotting the ordered pairs. So in this example, we have our x's as our domains, and we're going to determine what the range would be in each of these equations. So for our first example, we're going to have 2x plus 1. So 2 times negative 2 plus 1. Because we have negative 2 as our domain, we're putting it in for x. Then we're going to determine what our y would be. 2 times negative 2 is negative 4. Negative 4 plus 1 is negative 3. So our first set of ordered pairs is going to be negative 2 for the x, negative 3 for the y. So we created an input-output table that would be for your homework tonight. You can do your T. We formed our ordered pairs. And lastly, when we're done with this table, we're going to plot them on the graph. So in our second one, we're going to have 2 times negative 1 plus 1. 2 times negative 1 is negative 2. Negative 2 plus 1 is negative 1. So our second set of ordered pairs is going to be negative 1, negative 1. Next, plot in 0. 2 times 0 is 0, plus 1 is 1. So our next ordered pair is 0, 1. Then I'll plot in the 1. 2 times 1 is 2, plus 1 is 3. Our ordered pair for that is 1 and 3. And finally, 2 times 2 is 4, plus 1 is 5. Oops. Now you'll go to your graph and plot each of these points. So negative 2, negative 3, negative 1, negative 1. It's not going to plot for me. So notice after we plotted the points and connected them, which I'm going to ask you to do, you notice that they formed a line. When you have a function, which was the 2x plus 1, when you plotted those points, those ordered pairs, it formed a line. So that is known as y is a linear function of x. This is called a linear function. See in your notes, linear function. A linear function is a function whose graph is a line or part of a line. Not all graphs are lines, nor do all graphs represent a function. So yesterday in our notes, we discussed how to determine if it was a function or not. And recall that the domain can only be paired with one of the ranges. The domain cannot repeat. So we could tell that by looking at the domain listed here in our table. But we're going to learn today how you can look at a graph just by looking at plotted points to determine if it is a function as well. Okay, so using the previous example, we're going to determine what our range is going to be with this function. I'm going to pause the video and I will set it up. We'll put the ordered pairs and we will plot it on the coordinates. Okay, you'll notice again that this function is a linear function because once you plotted the points, it formed a line. Check your answers to make sure that your range is correct. If it formed a line, then you know that your domain and range are correct in this example. So y is a linear function of x. Okay? We'll pause this one, work on this one together, and come back and check our answers. So that okay, so again, check. We know this is correct because also you can see there's a pattern in your range. You have a -6, -3, 0, 3, and 6. So again, you can make your input-output table like this. Determine what your range is by the function given and plot your points. Pause this one. We'll come back and check with this one. Notice that we have 5/10 times x plus 1. Another way, if it would make it easier, you can do 1/2 x plus 1. Those are the same equations. Take your time to determine what your range would be. Okay, notice on this example, in this function, we have 0.5, as we talked about, being the same as a half. So notice when we multiply 1/2 times its reciprocal, -2/1, that's going to equal a 1, and it will be a -1 plus 1. In the second example, we have 1/2 times -1. Anything times 1 is itself, and it's going to be a negative. So -1/2 plus 1 is 1/2. So just be really careful. Remember the rules that we've been using and carry them over to determine what your range will be. Okay, I'll pause this one and we'll work this one out and plot it. Okay, again, when you have 5 minus whatever the domain is, 5 minus -2, remember we add the opposite, so that would be 7. And again, you can see a pattern, and you can check it, but this is also a linear function. Okay, note on this one. To determine what our range is going to be, it's going to be the opposite of whatever x is. So remember, not only can you say that this is known as a negative, it's the opposite. So the opposite of -2 will be 2. The opposite of -1 will be 1. Opposite of 0 will still be 0. The opposite of 1 would be -1, and the opposite of 2 is -2. And here it is graphed. Again, another linear function. Okay, let's note on F, we have a new one. So determine what y is. I put the whole thing in that example, but determine what our range is going to be. We're going to plug in -2. Now notice on this example, I have -1/2, and I'm going to use -2. So I'm going to put that again as an improper. That's its reciprocal. When you multiply anything times its reciprocal, it's always going to be 1. And it's going to be a positive 1 because a negative times a negative is a positive. So that's going to be a 1 plus 1. Your range is going to be 2. So -1/2 times a -1, that's going to be a positive 1/2. Anything times 1 is itself, and it's going to be a positive 1/2. So a positive 1/2 plus 1 is 1 1/2. -1/2 times 0 is going to be 0, plus 1 is going to be 1. -1/2 times 1 is going to be -1/2, plus 1 is going to be 1/2. And then -1/2 times 2/1, again, that's its reciprocal. So it's going to equal 1, but it's going to be a -1 plus 1 will equal 0. Now I'm going to write down each of the ordered pairs. Again, check your graph. Make sure you plotted each one correctly. And this is also a linear function. So if you have a word problem and you need to write and graph a function, I'll give you an example of one. You're running a marathon. You run at a constant speed of 9 miles per hour. Write and graph a function that describes the event. Remember the formula for distance. So the situation can be represented by the function y is going to equal to 9x. What you have been accustomed to is distance is equal to rate times time. And that's the same thing we're going to use, but we're going to be discussing the domain and the range. So y is equal to 9x, where y is the total distance you have to run, and x is the time in hours, just like it is in the formula that you're accustomed to. So if we were to plug in and do, instead of ordered pairs, if I had 0 for time, of course, 9 times 0 is going to equal to 0. So you didn't go anywhere without any time. In our second, y is going to be equal to 9 times 0.5. This you could do in your head. 9 times 5 is 45, but note the decimal. So y is going to equal to 4.5. So in the time, if you took half a minute, you would have gone 4.5, or half whatever your time is going to be used. So in our next formula, if we plugged in for time to be 1, 9 times 1 is 9, so your y will equal 9. Lastly, y again is going to be the total distance, so 9 miles per hour times 1.5, y is going to equal 13.5. So let's recap this one. You have been given a word problem that talks about running a marathon. You run 9 miles an hour, and you need to determine what the distance is going to be. So we plugged in a certain amount of times to determine what our distance would be after each time. Distance is equal to rate times time. 9 miles per hour was our rate, and then we plugged in the time to determine what the distance would be. So if you were told to plot this time, you would plot it on a coordinate grid, just as we've done in the previous examples. Lastly, you're going to ask to tell whether the graph represents a function of x. Now, we discussed this at the beginning of the lesson. So as we're finishing up this lesson, we're going to discuss how you can determine if it is a linear function by just looking at a graph. So let's look at our first example on here. On this example we have. Notice that when you have a line, and this is a linear function, in order for this to be considered a function, each of our domains had to be different. So for example, this ordered pair could be 0, 0, 1, 1, 1, then a 2, 2. Notice that as this is being plotted, by looking at it, each of the domains are different. In this example here, let's look to see if each of our domains would be different, so they would be a function. So in this example here, I can tell that this is not going to be a function, because in order to plot this point, I had to use the -3, 1, and the -3 for the 5. So this is not considered a function. In this example here, this is a function, yes, because I only used the domain one time. Here it is -4. Then I went up 1. Then this was over a little bit more than -4 to go up. Let's see on this example right here. Let's discuss, is that a function or not? If in this example right here, this was a straight line, then it would not be a function. But it seems to be moving a little bit, so each of the domains are different. So yes, this is a function. we have this example right here. Let's talk about this. Is this going to be a function on this example? So this is a function. Let's say I had a graph that it looked like that. And here was my x and y axis. This would not be a function. Because see, I had to go right here to go down here, and also a 2 to get here. So this would be not a function. You can also do a pencil test. And if you take your pencil and you drop, and pretend this is a pencil right here, and you were to drag it along the x-axis, if it was to cross over more than one point, then it would not be a function. So again, you can tell by looking at a graph at the function to make sure it only uses the domain one time. Okay, it's a recap for this telling whether the graph represents a function or not. You need to be able to make sure that the line does not cross the x-axis more than once.